Okay, so in terms of the meta-mathematics, we've kind of taken care of two of the things that we mentioned kind of were out of the four that we wanted to discuss. We have a language in which to talk about mathematics. We have the language of mathematics. We've talked through that. And we have also had a long discussion about what it is we're trying to study, this like Platonic object that we're trying to study, or just kind of as an example of just objects which we might want to study in general. You might have noticed at this point that there are things missing from our object of interest, right? We're talking about the natural numbers, but I mean, there's no such thing as subtraction in our world. That would be a different object. We would be studying the integers at that point. But our main example, but the thing is that the natural numbers are simpler than the integers. And so if we come up with some kind of incompleteness theorem about the natural numbers, then it would also apply to a system like the integers. So the simplicity of the natural numbers is actually a boon and not something bad. But in any case, it's our main example of like an object which we want to learn truths about. So we've discussed those two things. And now what we're going to kind of turn to is the discussion of how do we discover truths about this object? We know how to talk about it. We know what it is. How do we learn about it? How do we learn it? And to answer that, I want to begin with the more general kind of question about us. How do we as humans learn in general? And so I'm not going to claim to know the full answer to that, but I do know of some kind of skeleton that I can identify regarding how we reason and deduce and learn. And so basically, it goes like this. Regularly, we make deductions about our own reality. And the way it goes is that it's very simple. First, I observe something that occurs in reality. And then what I do is I observe some kind of like causal phenomena related to that occurrence. And then from that, I can deduce, given the occurrence of the thing and the implication regarding that thing, some new thing that is implied. Now that's a little abstract, so let me give an example. So here's just a line of thinking that you might have done at some point in your life. So here's an example. I failed a class. That's the thing that happened. That's an occurrence that happened in reality. I failed some college class. If I fail the class, and here's the implication now, this is a causal phenomena that you know is a thing. If I fail the class, I can't sign up for the next class. And so I have what? I have that I failed the class, and I know that if I failed the class, then I can't sign up for the next class. And therefore, I have a new thing. I cannot proceed to the next class. This final line, I can't proceed to the next class, is deduced from, one, this thing that I've observed happening, and two, this causal kind of rule that I'm aware of. I put these two things together, and I get a third thing that I didn't have before. That is a deduction. I've deduced this sentence. Here's another example that kind of builds off the first one. Suppose I also know this kind of causal rule. If I can't proceed to the next class, then I can't graduate in 4 years. Well, I already know that I can't proceed to the next class, therefore I can't graduate in 4 years. And so that's a second deduction that I can get. And so this is, I think people will hopefully agree that this is really a core component of how we think. This kind of deduction method is how we kind of reason through stuff. Whether we were taught logic formally or not, this is sort of a skeletal like kind of form that kind of underlies, I think, all kind of reasoning of any sort. Maybe I'm wrong about that. I'm really not sure. It just kind of seems that way to me right now. And the reason it maybe seems that way to me is because I'm a computability theorist. And so kind of, there's a clear connection between what I just described here, this process of deduction, and our model of computation in general. What happens? So we talked earlier in our physical computations video about just you existing as a human as like an ongoing computable process. And that setup is basically that the store here, S, is the environment, is basically the entire universe, and that you are, have some focus in that universe, and that you're taking in information from that universe and then making decisions based on that, right? And that is kind of your fundamental existential loop that you're constantly on as you sit here breathing and watching my video. So it seems like, this deductive process is sort of at the core of whatever's going on in this box here. In the decision-making process itself, it seems kind of like the way that you kind of use what you know already and what you've learned before in order to get to a point where you have a decision to make and a thing to do, a way to interact back with your environment, it's this kind of thing. right? So I think that this kind of idea of deduction, this very simple kind of idea, is really at the heart of kind of human computation. Not human computation as in human pen and paper computation, but human computation as in your conscious existence right now. It's kind of it's kind of a basic, it's kind of like a basic system that underlies how we process reality and how we form and reform our ideology in real time. So this is sort of this is sort of a big, I think, an important part of how we process the world. And this is really going to be, this is pretty much going to be the entire definition of what a proof is mathematically. Mathematics is just kind of a distillation of this process in the abstract. So let's see that. I can abstract this, so let's do that. So we can view this process abstractly. So I'm going to define a deduction, otherwise known as a proof, as a finite sequence of statements which obey the following set of rules. So here are the rules. At any time, I'm allowed to state something that I already know is true. So I'm allowed to always do that. And then 2, if 2 of the things that I've already said have the following form, that is A, that's the thing that's true, and A implies B, that's something else that I know is true, but it's an implication specifically that I know is true. It's a causal relationship. So if I know A, and I know that A implies B, then I'm allowed to assume that B is true. So that's really the core of this. This is what I mean when this is what I was talking about before, but in symbols. If I know that A implies B, and I know that A, then I know B. Right? That's exactly what I did up here. Let's look at this example one more time. I failed the class. That's A. If I fail the class, then I can't sign up for the next class. That's A implies B. Right? B is I can't sign up for the next class, and therefore B. That's what's going on. And then modus ponens happens again here. I didn't say what that was yet, but here's another one. You know, here's basically a B implies C. Well, I now know B, and I know that B implies C, therefore C. And so it's a chain of these deductions. This is like one step of a deduction, and this is the second step of a deduction, and I can kind of do multiple steps of a deduction to kind of make a chain that leads me somewhere that I maybe couldn't have even imagined to start, right? So this idea here has a name. It's called modus ponens, which is Greek, I think, for method of affirming. This is the rule. It's the only rule. This is proof right here. This is really all there is to mathematical proof, and to some extent, in that sense, mathematics in general. All of mathematics can boil down to sequences of things like this. Just implications. Implications and conclusions. My conclusion basically is that a real-life proof or deduction, whatever you want to call it, this kind of process that you're very used to doing, that I'm describing, is nothing more than a finite chain of repeated applications of modus ponens, which are formed by pulling the things you already know, pulling from the collection of things that you already know are true. So you have in your head right now a bunch of things that you know are true, that you have learned throughout your life, both from a combination of observations of the world and from deductions, from other deductions that you've made previously. And so the way that you process, you know, what I'm saying to you right now is you're just doing modus ponens over and over again, right? So that is, to some extent, computation, right? You can already kind of taste it. It's there, you know, there's computation. But let's not confuse ourselves with that. Let's just kind of think about this as a new thing and keep going. So let's bring mathematics into this now. So what's the difference between mathematics and this process of computation or deduction, as I'm calling it, that's happening in reality? Well, the difference is that in order to, this step here, basically, at any time I'm allowed to state something that I already know is true. How do I know that something is true in reality? I know that something is true in reality. Most things that I know are true in reality, I know that they're true because I've observed them multiple times, right? For example, the sun rises every day. How do I know that? Because it's risen every day of my life so far. And so I can only assume that it's going to happen tomorrow. This is kind of a principle of induction philosophy thing. That's most of where we get these truths from. In other words, we have a material reality from which we can pull things to do this deductive process with. In mathematics, that's not the case. We don't have mathematics, this thing n. I can't observe anything about n in reality because n doesn't exist in reality. This Platonic entity called the natural numbers exists in its own plane of existence. It exists somewhere else. And so I can't just observe things about it. I've been using it, so there are things that I've been assuming about it. But what we basically need to realize is that since we don't have a reality to pull from, we have to decide for ourselves, in advance of doing any deduction about it, what is going to simply be assumed to be true. So we have to decide on a few core basic assumptions in order to get started, in order to learn truth about the natural numbers. That's kind of a concession that just has to be made. There's no other way. If we want it, at least there's no other way if we want to do this process. If we want to basically do to the Platonic realm the stuff that we're doing in reality. And so we have to settle on some basic assumptions, and those basic assumptions are called axioms. So those are the basic assumptions. And of course, they're going to be formulas, right? So since we're speaking in the language of mathematics, when I talk about basic assumptions and I talk about any of this stuff, I'm really talking about well-formed formulas, right? The language of mathematics, language of number theory. So to summarize, what have we done so far? I've kind of observed this sort of system of proof and deduction that we do in real life, just kind of in real time as we exist. I've observed kind of a core kind of rigorous skeleton of our own thinking generally. And I want to take that to be essentially what proof is. I want to take that as the definition of mathematical proof, and I almost can. The only thing I have to do is I have to kind of decide on a set of axioms to start me off. So any deductive system for discovering truth about the natural numbers must begin with settling on a set of whiffs phi, for which we simply assume that phi is true for the natural numbers. And so I'm going to denote a set of axioms as usually like the capital Greek letter gamma or something like that. And so a set of axioms is what I'm going to call an axiom system. So that's that. And now I'm ready to finally define formally what a mathematical proof is, which is kind of the same thing I've defined already in reality, just stated in terms of math. So here's the definition. Here's the definition of a proof. So we have a set of axioms gamma, and we have a sentence phi that we want to prove. Phi is the thing we want to prove. And remember, sentences are the things that we kind of assume might or might not have proofs, the things that might be true or false, right? So a proof or deduction, those mean the same thing, a phi, is a finite sequence of sentences which obey the following rules. So it's basically a sequence of formulas. It's just a sequence of formulas. You can almost think of the set of proofs as sort of a formal grammar that you're putting on top of the set of well-formed formulas, as like the alphabet, kind of. You can't really think of it that way because that would be an infinite alphabet, which is not allowed, but it sort of is that anyway. In any case, a proof is just a finite sequence of sentences. And and that finite sequence has like a structure to it. It has to obey the following rules. So number one is that axioms are allowed to appear anywhere in the proof without any kind of justification. You're allowed to have an axiom anywhere in the sequence. That's fine, at any point. Two is the modus ponens part. If psi is a sentence in the proof which isn't an axiom, then there has to be some other sentence alpha such that both alpha and the formula alpha implies psi appear as sentences earlier in the proof. In other words, I have to have the two components of modus ponens that apply to the thing that I want to write down before I can just write anything down. I cannot write psi down until I have something that implies psi and that implication is true, right? I have to have some alpha, which I already know is true, that implies psi in order to write down psi. That's the main rule. That's really pretty much the only rule. 3 is hardly a rule. 3 just says that phi has to be the last thing appearing in the proof. So I mean, the phi is more or less just a kind of a standardizing thing. It's not really deep or important. But that's it. You know, I mean, if you compare that definition to the one I gave up here, it's basically the same, except with talking about whiffs and stuff, right? I did, again, just to kind of repeat what's up here. What's a proof in real life? What's a deduction in real life? It's a sequence of statements following the set of rules. Basically, the two rules are that any time I'm allowed to say something I already know is true, And I'm allowed to say a new thing if I have an old thing that I know is true and an implication about that old thing. Then I'm allowed to say what the implication is. That's all I'm saying down here. It's just in fancy math terms. So that's a proof. Now you're probably a little surprised because if you've ever taken a class on proofs, you've learned all kinds of like proof methods. You've got proofs by contradiction, you've got proofs by induction, you've got proofs by contraposition. You know, I mean, essentially you might be thinking that what I defined here is just a direct proof, and that's true. This is, all proofs are direct is essentially what I'm saying here, assuming that this is a powerful enough proof system. But that is my claim. I'm claiming that all of that stuff is just fluff. At the end of the day, it's really this that constitutes a mathematical proof, and to some extent also constitutes what mathematics is. What is mathematics if not proving things? And so this is a very basic statement about fundamentally what we're doing with math. So if the sentence phi is provable from gamma, i.e. it has a proof, which uses those axioms, then we say that gamma proves phi. And we write this notation, gamma with like a single bar, like a line with like a single thing coming out, phi. This basically, we read this, gamma proves phi. That's what we say. That's how we read this. So that's it. That's the definition of a proof. This is our formal proof system. There's three basic questions that we need to ask before we can continue. So we need to flesh this out a bit, and we need to ask the following three questions. Question one is, what makes for a good set of axioms? I haven't talked at all about what the axiom system is. Like what is going to make for a good set of axioms? Right? Should I just allow any set of statements to be axiom? Probably not, right? So we have to have that discussion. Like, what are we going for when we write down a set of axioms? Like, what should we think of as good, and more importantly, what sets of axioms should be invalid, right? Two, and that this is something I kind of asked already. Is the system that I just described for proving things actually powerful enough? Because I think you'll note this is very minimal. This is a very minimal system. So how do I know that this is powerful enough to prove anything that I want to prove, or anything that I should be able to prove? Furthermore, what should I be able to prove? So we have to kind of have that discussion. And then the third discussion we have to have is, does proof actually imply truth? We never had that discussion. We never talked about that. If I have a proof of something, is it true? I mean, we're going to have to talk about that. So before talking about any of these, I want to bring in a bit of computability theory, and I want to define another crucial decision problem. And that decision problem is proofs with the subscript gamma. So it's actually not one decision problem. It's a different decision problem for any set of axioms. So given a set of axioms gamma, proofs of gamma is a decision problem, and it's simply the decision, given a sentence phi, is it provable? In other words, it's this question. Does gamma, let me try that again. Does gamma prove phi? This is the decision. The decision is, given a sentence, is it provable? Not is it true, is it provable? Because we haven't had that discussion yet. What is there an equivalence between truth and provability? I don't know. Does proof even imply truth? I don't know yet. So I think we should have that discussion first, even though it's labeled 3. I'm not actually going to do these in order. I think I might even do them in the exact opposite order, but in any case, there's an obvious thing that I should probably address immediately, which is that you've seen a decision problem like this before. We mentioned that there was another actual star of the show, and I still stand by that the other version of this thing, or the similar thing that I defined already, is the real star of the show. I'm looking for a place to write it. But, we have this decision problem, and we've also stated another decision problem, which is this one. Given a sentence, we can ask, does some axiom system prove it? We can also ask the more, pertinent question, is it true? Right? And so this was the decision problem pertaining to what I defined as truth. And so probably to end the video, it would be best to compare and contrast these obviously two important decision problems, which we are going to be relating with the rest of these videos. The comparison between these two is kind of the topic of the rest of this. So let's consider this third question. Does proof imply truth? In other words, and which obviously is equivalent to the question, how do these relate to each other in the this to this sense? So suppose that gamma, this set of axioms, is a suitable axiom system. Now, suitable is its own vocab word. It has its own definition. What I mean by suitable axiom system for the natural numbers is simply that the things in here, the axioms, the things that I'm assuming are true, are actually true. Now, that might sound like a weird thing to assume right off the bat with this discussion that we're having, but keep in mind that it is not exactly the same. That it's not exactly the same assumption as the thing that we're talking about whether we can assume. What we're talking about here is does proof imply truth, not are the axioms true. Although we're going to see that the answer to one is going to kind of answer the other as well, because it's not going to be a satisfying answer for reasons that we'll get into. So basically, the answer is we can only assume that this is yes. And the reason for that right now is just the way that I've presented this material. It's the Platonic bargain. Remember, we're simplifying a lot of this stuff for ourselves by assuming that the natural numbers are this like Platonic entity existing in its own realm, in which truth is already predefined for it. Truth already exists. We can only reach for it, and we certainly don't know for sure anything about it. We're just reaching towards it. And so that the consequence of that Platonic bargain, you could call it the downside, is that there is no way to define truth mathematically. Once we break the Platonic bargain and define the natural numbers as a specific model within some broader theory, then we can define truth for it explicitly. But right now, the consequence of the Platonic bargain is that truth is simply an ideal that we can reach for. And we are going to assume that our proof system that we derive, whether or not it's powerful enough to prove anything, what it does prove, we're going to assume it is stuff that's actually true, assuming we started from axioms that were actually true. And I think that's in the defense of the ancient Greeks, that is completely reasonable. Why wouldn't that be reasonable? I mean, it seems like my deductions work in real life. The deductions that I make day by day in order to survive, those work. So why shouldn't these work? So I mean, it's perfectly reasonable to assume, given how innocent our proof rules were, that a proof system should at least imply true things if I started from true assumptions. But the downside is we can only assume that. So the answer to this third discussion is yes, but we are forced to just assume this. But we are forced to just assume by the Platonic bargain. So this is the downside of that. It simplifies the discussion quite a bit, but it also makes truth simply something that we have to just assume is predefined, and that we are correctly reaching for it in this way. But again, we will break that bargain at the end. So that's the answer to number 3. And so let's think about how that relates back to this discussion about these two decision problems here. And also state, for the record, finally, the real question that we've been working towards asking and answering this whole time. So let's bring in our decision problem for this. So we've got these two decision problems now. Proofs of gamma, where gamma is an axiom system, and truth of the natural numbers, where the natural numbers is this mystical object that just exists that I'm trying to discover truth about. Now, the discussion we just had of point 3, that proof does imply truth, amounts to assuming that this decision problem is a subset of this decision problem. Everything in here, assuming that this is a suitable axiom system, right, assuming that these axioms that I think are actually true, that is going to be a subset of truth of n. That direction is a given. And it will continue to be a given after we have broken the Platonic bargain. But in that case, it will be a theorem, and it will be called the Soundness Theorem. I'll probably reference this theorem again when we actually get to that stuff. But that's one of the kind of 4 major theorems related to the incompleteness theorem that I think are worth mentioning by name. The Soundness Theorem is what says that our proof rules are good, in the sense that they at least prove true things. It's a sound set of proof rules. But the other direction is obviously what we're more interested in, and it's the more philosophically interesting direction. We know that proof implies truth, sure. We've decided to assume that. But the other direction is really what we've been pursuing to talk about this whole time. Does truth imply proof? So what we want, obviously, I think you'll agree what we're going for is we want an axiom system, of course, in which everything that's true is provable. I don't want to miss anything. If something is true about the natural numbers, I want to be able to prove it. And so we want an axiom system where everything true is provable. And so that is the question to ask. That is the big question. Does there exist a suitable good axiom system? I haven't defined what it means for an axiom system to be good. We have to have that discussion still. But is there an axiom system such that truth is a subset of proofs? In other words, they're equal. In other words, is in which everything that's true is provable. In other words, and I'm gonna give this a name. There's going to be several ways to say it, but is there an axiom system which fully axiomatizes the natural numbers? Is there some set of axioms that I can write down that is a reasonable set of axioms, a good one, of true things, which actually makes it so that I can prove everything that's true about the natural numbers? That is the question to answer with Gödel's first incompleteness theorem. Gödel's first incompleteness theorem will be a yes or no answer to that. And so that is where I'm going to end the video. And in the next video, we will address one of the two other questions. I'm really not sure which one.